Welcome to this video about optimizers in PyTorch. In my previous videos, I talked about how to create a simple neural network using PyTorch and how to use different activation functions again in PyTorch. In this video, we'll talk about some important optimizers available in PyTorch. Not go too much into the theoretical aspect of each of these optimizers, but provide a practical walkthrough. The notebook used for this video will be available on GitHub and you can access the link in the description box below this video. Let's get started. The first part of this notebook will look very familiar to you if you have watched my previous videos on PyTorch. First, we import the relevant libraries, get the training data in a CSV format, do some pre-processing on this data, which includes min-max normalization of the data, and finally splitting the data into training and validation dataset. Next, we define a function which allows us to train the model. This function takes the model object as an input along with an optimizer. The rest of the function will look very familiar to you if you have watched my previous videos, especially the one which involves creating a simple neural network. Essentially, we loop through various epochs and batches, get prediction from the model, calculate the loss, and then back propagate to update the model parameter based on the loss that we have calculated just now. Next, we define a function to calculate the AUC scores. Now let's start talking about various optimizers available in PyTorch. The first is stochastic gradient descent. Stochastic gradient descent is essentially similar to gradient descent, but instead of using the entire training data, we use a single training example to update the model parameter in each iteration. Let's look at how we can use this in PyTorch. First, we define a very simple model with just one linear layer and a sigmoid activation function. The reason why I've kept this model so simple is so that we can focus on optimizers and how to use them in PyTorch. Next, we define the optimizer here, which is stochastic gradient descent. We pass the model parameters and define a learning rate. Now, since stochastic gradient descent using a single training example for each iteration, I have defined batch size as 1 here. We'll train it for 3 epochs. The training data that I have is quite large and it might take a lot of time for us to train using a batch size of 1. That's why I have taken a subset of the training data, essentially only 10,000 examples, so that I can just demonstrate how stochastic gradient descent with a single training example work. You can see we train the model and then calculate the ROC AUC value here. So the AUC value that we get here is 0.838. Now, one thing to note here is that this notebook will calculate AUC value for different optimizers using PyTorch. However, please don't use these as a reference to compare various optimizers and make a value judgment of which optimizers is better. You might have to try this out on your own dataset and your use case to find the best optimizers for your use case. Okay, coming back to stochastic gradient descent, let's talk about one of the shortcomings for SGD. Since we use a single training example, it is prone to oscillations, which means that we do not move towards the local minima of the loss function in a straight line fashion, essentially not in a monotonic fashion, which can lead to slow convergence and longer training time. So to overcome this problem, we can look at the next optimizer, which is mini-batch stochastic gradient descent. Mini-batch stochastic gradient descent gives us a middle ground where we do not use a single training example as in stochastic gradient descent or use the entire training data as in the case of gradient descent. We use small batches of data to update our model parameter so that this data can fit into memory and we don't face the problem of training with very large data sets. Let's look at implementation of this. The code here is very similar to the previous example that we saw for stochastic gradient descent. The only difference is that we have used a batch size of 1000 and I've used the entire training data here, since we are not limited by the slow training process for stochastic gradient descent. You can see the model has been trained and then I've calculated the AUC value here. Now let's talk about a couple of shortcomings of this approach. First is that we might require tuning of the mini batch size. While this might not be required always, but it can help improve model performance. Second shortcoming is that convergent path might still oscillate while not in the same way as stochastic gradient descent. So to overcome this weakness, we move to the next approach, which is stochastic gradient descent with momentum. You can think of momentum like a weighted average where we have some weightage assigned to the previous updates of the gradient so that we have a smooth gradient descent over the loss function and we reach the local minima. Let's look at the implementation of this. In this case, I have kept the batch size as 1. However, that's not something that you need to do. You can keep a batch size of any amount that you have. But if you define a momentum parameter that allows you to use stochastic gradient descent with momentum, I've used a momentum parameter of 0.5. Then I've trained the model and calculated the AOC score. Now, one of the things that you might have to do is tune this momentum parameter, try a few different values to see what works well in your use case. The next optimizer that we'll use is Addergrad. In case of Addergrad, instead of using a single learning rate for all parameters, we have different learning rate for each of these parameters where they start with a large value and slowly decrease as we move closer to the minima. So it essentially helps us to reach the minima in a quicker fashion, but as we come closer to the minima, the updates that we'll have is small so that we are able to get to the local minima. Let's see how this is implemented. We have the same model structure. We use Addergrad here with model parameters and a learning rate. We define the batch size, train the model and see the AOC value. Now, one of the problems with Addergrad is that if the number of training iterations are too large, then the learning rate can become too small, which means that after a point, the learning might slow down or even stop. So to overcome that, we can use RMS-prop as an optimizer. RMS-prop uses a moving average, which helps in keeping the learning rate from becoming too small. Let's look at the implementation of this. We define the model structure again. RMS-prop has been defined as optimizer. We train the model and calculate the AOC value here. The final optimizer that we'll use is ADAM. ADAM combines the benefit of momentum as well as RMS-prop, and it is one of the most widely used optimizers for neural networks. The implementation of this is very similar to the previous examples that we have seen, where we define the model structure, we define ADAM as an optimizer, we train the model and calculate the AOC value. So I hope this was helpful for you to understand different optimizers available in PyTorch and how to use them. If you found this helpful, please press the like button and subscribe to my channel. If you have any questions, feel free to put them in the comment section. Thank you for watching the video.